Now we're gonna talk about genomic selection and hopefully all the concepts that we have learned in the course are gonna help you to understand better how we can use genomic selection in the breeding program. So the first thing that I want to mention is that remember that we mentioned or we talk about association mapping and QTL analysis when basically we're interested in identify the genomic regions that have association with the phenotype, and that it's really useful in traits that are controlled for a few number of loci, and the goal is try to integrate those QTLs that we identified with these methodologies into the germplasm that we are using in the breeding program. But as hopefully you now can see, when a trait is controlled for a lot of loci across the genome, maybe it's a more useful approach use genomic prediction or genomic selection. And here in this slide that is from Dr. Bernardo, he preferred to use genome-wide selection instead of use genomic selection, but it's the same. But yeah, basically he preferred to use genome-wide selection because as we use genome-wide association, so basically he think that we shouldn't like change the first word. But it's the same. Just I want to mention that because in some papers you are gonna find a genomic selection and others a genome-wide selection. So, and now we have the model. So that is the simplest model for genomic selection. And basically you can see here that we have one component. We have three components. So the first ones are the fixed variables that we can include in the model, and in those fixed variables we can include for example the subpopulation information. We can include QTL information, so if we have some major QTLs we can use that information as fixed variables. And also we can use environments if we have that information, if we want to use that information in the model. But usually we just use the random effects, and those random effects are the effects for each marker. So you can see here that we have the incidence matrix in the fixed effects and another incidence matrix in the random effects, and the incidence matrix just are logical matrix that basically connect or are the relationship or show you the relationship between the, in this case, fixed effects and the response variables. And here in the random effects show you the relationship between the response effects, that is the phenotype of each sample, and the effects of the molecular markers. So again, yeah, in the model we have fixed effects and random effects, and the reason why we treat all the molecular markers, at least that we have a major QTL that we can use that molecular marker as fixed effect, but the reason why we use usually all the markers as random effects is because nowadays the number of markers is bigger than the population size, so we cannot take 1 degree of freedom for every single marker because the population size. So that is why we have to treat all the markers as random effects. And with that information, hopefully you can see that when we don't use fixed effect, the formula to estimate the genomic values in the populations are equal to the incidence matrix that again show you the relationship between the response and each marker effect, and And basically, if we do the linear regressions, we can estimate the alpha value for each marker. So we have, again, incident matrix to connect the phenotype and the marker effects in the formula. And we have to add the marker effect for every single marker, and after add every single effect in the genotype of one sample, that is defined as the breeding value or genomic value. Yeah, so remember, I think that I mentioned that previously, but remember that to estimate the alpha, that is the allele substitution effect, we have to do linear regressions of the phenotype and the genotype of in the population in the population. So here you can see that the codes that we use, we can use two different codes, I would say. So we can use 0, 1, and 2, and as you can see, that represent the number of copies of the allele A1 that we have. So in the homozygous A2 we don't have any A1 allele, so that is why the value is 0. And here we have in the heterozygous we have one A1 allele, and now we have the code that is 1, and here as we have two A1 alleles, so we have the number 2. Another way to, or maybe the most common way to code the genotype is -1, -1, 0, and +1, and again that is to represent the copies of the P allele, or that is represented with the in this case with A1. So basically the increase in the slope, that is the increase in the phenotype, has a relationship with the increase of 1 unit in the x-axis, that in this case is the allele 1. And now with that in mind, again, hopefully now you can see that basically the breeding value or genomic value, it's equal to the alpha values and basically the marker effects of the sum of all the marker effects in every single sample. So that it's the breeding value. But the point now is how or which population we use to estimate those breeding values. So that is why we need to use a training population, and in that training population we need to have the phenotype and the genotype of the population, and like in this population we have as the phenotype and the genotype, we can do the linear regressions and we can estimate alpha for that population. And after we estimate those alpha values for every single marker, we can use a testing population, and that testing population we just need the genotypic information of the genotype of every single sample, and here basically we can use the alpha values or the allele substitution effects that we estimate in the training population, and we can predict the breeding value of this testing population. So that is why it is important that the training population have a relationship with the testing population, because if the relationship is so weak, if the allele frequencies between them it's so different, as you can imagine, the alpha values are gonna be useful for the training population but not for the testing, if the testing doesn't have any relationship with the training population. And again, this is the most basic model, and if you are interested to go a little deeper into the model, you can visit this video from Dr. Rex Bernardo, and in that video he explained really good the model and other concepts that if you are interested a little more in the model and the statistics behind a genomic selection, he's the person that you have to listen. So I encourage you that please visit this link and watch that video. That is really good. And now, again, just to show you a little bit, or to remember you the difference between marker assisted selection and genomic selection. Here we have the traditional mass when we need to collect the genotype and the phenotype, and with that information we can run a genome-wide association, and we can identify or QTL analysis, and we can identify the genomic regions in the genome that have association with the target trait. Then we have to design some molecular markers, and with those molecular markers we can start to do selections in early generations. And basically what we want to do is try to stack the samples that have the good QTLs in their genome. So that is the traditional mass. But with genomic selection, the approach is different. We are not interested to identify the regions in the genome that have association with the phenotype. We just want to estimate the effect of every single molecular marker. And then that we estimate the effect of every single molecular marker, we want to predict the genomic value in the samples when we don't have a phenotype. And as you can see here, the idea is that in theory, both models, in case that we can identify all the regions, that means that we have at least one molecular marker that is in LD with all the QTLs that control the phenotype. So both methods should be equivalent, but of course the approach is different, and the number of in the real life, the number of markers that we can use with a marker assisted selection, it's limited because time and cost in the lab. And another variable that we have to assess in genomic selection are the different models that are available for estimate the breeding value. So the most popular, I would say, that is RRBLAB, and is the one that we're gonna use in the hands-on section. But like in general, there are several software approaches, statistical approaches to estimate the genetic value. You can see here that most of them tend to have a really similar accuracies or predictive ability. So that that is why I guess RBLAB is still the most popular, because it's kind of straightforward to use. But in theory, there are models, especially the Bayesian models, that could be better in theory, because in Bayesian analysis you can set what is the some prior information. So that prior information that you can set in a Bayesian analysis for estimate the breeding value has relationship with the variance that can be explained with the molecular markers. So with RRBLAB, we can basically define, or with the model define, that all the molecular markers has an effect in the phenotype, that we know that it's not true, that is wrong, that is a wrong assumption, but still the model works pretty well. And in Bayesian analysis, we can set, for example, Bayesian base C estimate that most of the marker has a effect in the phenotype equal to 0, and there are just some a small number of markers that have an effect in the phenotype. So if you know the genetic architecture of your trait, if you have a lot of QTL information, and you know that the trait that you are interested to predict the breeding value, it's controlled for few alleles or few genes or QTRs in the genome, maybe base C it's a good alternative. But again, a lot of papers have reported that the model maybe is not the most important factor that affect the accuracy of prediction. And another concept that you have to take into account when you are working with a genomic selection is the population structure. Um, so remember that in genomic selection, you have to estimate first the alpha values in the training population, and with those alpha values, you can predict the breeding value of a of a testing population. Um, and when you have subpopulations, it is gonna be difficult to use one of the subpopulations to predict the another one, because again the relationship between subpopulations it's not strong enough, so they don't share allele frequencies, for example. So that could be challenging if you use, in this case, subpopulation 1 to predict subpopulation 2. So one alternative to use both subpopulations is try to basically select uh, a percentage of subpopulation 1 and a percentage of subpopulation 2, and combine that those two like selections in a training population and estimate the alpha values for every single marker in that way. And here you can see that they have two, in this paper, two different traits. And basically here as validation, they use population 1 and to as training, basically to estimate the alpha values, they use population 1 and 2. And you can see here that the prediction accuracies were kind of good, I would say. But when they use the population 2 to predict the population 1, you can see here that there is a huge reduction of the accuracy. So again, the relationship between training and testing population is really, really important for the accuracy of the models. Yeah, and same here in this other trait. So that it's something that you really have to pay attention in your analysis. And then we have the marker effect. So again, we have to estimate with the linear regressions the effect of every single marker. And as you can see here, you are gonna see some regions that have or molecular markers that have a strongest effect or highest effect in the phenotype, but we are gonna use the information of every single marker to estimate the breeding values. And when you have the effects of all the markers, you just have to add the effect of every single marker in each sample. And doing that, you are going to estimate again the breeding value. And with the breeding value, basically it's the genomic value. So that is the genetic value that that line have for that specific phenotype. And in a perfect world, we want to have a correlation that will be close to 1. So a perfect correlation between the phenotype and the genomic value. But that it doesn't happen in genomic selection because, as you can imagine, there are like a lot of other non-genetic factors that influence in the phenotype that it's not possible to capture with the genomic selection models. But what we intended to do with genomic selection is select the best lines or other lines that have the highest genomic value. And if the model is good enough to select the lines or the correlation is high between the lines with high genomic value and high phenotype, in this example, that will be good enough to use in the breeding pipeline. And there are not a lot of papers that compare traditional breeding and genomic selection, but the consensus of most of them is that genomic selection tend to have a more or a higher genetic gain per unit of time. And in this study that paper is in maize, they compare the traditional breeding that they prefer to call, name here like a pedigree breeding, and basically they also use genomic selection. So here is genomic selection by line, and here is the traditional breeding. And as you can see here, the numbers that are involved are the highest genetic gain that they observe in the study. And as you can see here, just in this trait, and actually they make a mistake here because the highest value it's also in the traditional breeding. So just in these two traits, traditional breeding was higher or got a higher uh, genetic gain if you compare that with genomic selection, with the genomic selection by line. And that, or one of the reasons for that, is that for example, this is plant height, and this trait have a really high heritability, and in traditional breeding is really good or efficient in traits that are easy to measure and that have a high heritability. But when they do the comparison between more complex traits as a seed production, for example, they saw that genomic selection uh, seems to have a higher genetic accuracy, a genetic gain in the traits. So that it's good, and but the most important in the most important factor that can affect genomic selection or can like be beneficial for the breeding program is that genomic selection has the potential to reduce the time for breeding cycle. So genomic selection it's not gonna beat or it's not gonna be better than traditional breeding if per unit if you just consider if you use exactly the same by line. But genomic selection has the potential to reduce the unit of time using greenhouse, using the winter nurseries, or basically advancing the lines faster. So that is a great potential that have genomic selection. And that is why genomic selection is not the solution for all our problems, but it is helpful. So this is the breeder equation. So if you are not familiar with the breeding equation, so this is the genetic gain, and that is equal to the selection intensity, the accuracy of selection, and the additive variance in your population, divided in the general interval or the time that you need in your breeding program to do one breeding cycle. So genomic selection can increase the factors, the increased intensity of selection, the accuracy of selection, and the additive genetics in your population, and can reduce the time that you need in your breeding cycle. So that is why genomic selection has a big potential to increase the genetic gain. And and something that nowadays with the prices of genotyping that is important to take into account is that if get the genotype, it's cheaper to get the phenotype that you are interested. So genomic selection also it's a good alternative because it's not that genomic selection, it's not just that genomic selection has the potential to increase the genetic gain with the formula, with affecting every single element in the formula of the breeding equation, but also it has the potential to reduce the cost. So we're going to talk about that in the next presentation. This is the end of this video.